Welcome. Thank you, everybody. Excited to be here at Cloud Field Day. I'm Steve Tuck, co-founder and CEO of Oxide, and wanted to take you through today a little bit about Oxide's history, how we got here, what we are doing, and dive into the product a little bit more. The on-premises IT landscape today looks vastly different than what resides in the data centers of cloud hyperscalers. In the cloud hyperscalers over the past 10, 15 years, they've gone away from the rack and stack kind of kit car approach of enterprise IT. And they've started designing at the rack level. They've started incorporating hardware, software, co-design in the systems. But that technology is not available to those that run on-prem. When you're running on-prem today, you still have to pick a server vendor, a storage vendor, a networking vendor, an enterprise software vendor, some sort of software management tooling. And then each one of these companies ends up being their own SI. They're responsible for the integration of this. They're responsible for the upkeep. My co-founder and I experienced this very problem when we were at Joyent, running a public cloud. But unlike some of the cloud hyperscalers, while we had built our own sophisticated control plane, we were doing it on commodity hardware. We were doing this on Dell and Force 10, and then we were doing this on Supermicro, and then Arista. And at every one of these boundaries, we would hit inefficiencies that would cost us around performance, availability, and inability to debug the system. And this is not how the hyperscalers do it.
In what sense would you say that APIs are a second-class citizen? That's a statement in an app dev world that is all about APIs.
For sure. I think you have to look at kind of the different layers of the stack, but either bolted on or not well versioned, or having 56 APIs for just the virtualization orchestration stack that someone has to navigate against. So simplification around the API layer, having them well versioned, well documented, and an API first mentality has been a shift. That was not the case 5 years ago. That was not the case 10 years ago.
I do think that southbound APIs into the infrastructure for all that fun 12-factor stuff is like really underdeveloped. And I would agree that APIs, I think, they seem like an easy button and they're not.
That's right.
Right. So. But I don't know if second-class citizen.
Yeah, it might be a little strong, but again, not an API-first mentality, and that really shows up when someone rolls out a big new hyper-converged system on-prem, and the development teams are exposed to not being able to use the same automation and tooling they do in the public cloud. And so we look at the public cloud API kind of architectures and primitives as sort of the API first mentality. It's certainly the mentality we have taken. We'll talk about both from a developer perspective and also an operator, so that you have the ability to programmatically get the data out of the system that you need and understand what the system is doing.
Yeah.
Kind of like we want to put an API in front of everything, or API access in front of everything. And certainly that would be what you would find in Google's data center, Amazon's data center, Facebook's data center, because they need the automation. Right? When you are operating at scale, you can't afford to have the kind of personnel overhead required to operate these kit car deployments where you have 4 or 5 different enterprise vendor products not designed together. Of course, I'm sure you've heard similar anecdotes, but from our customers who really want to put their best engineers working on their products to go build and meet customer timelines, and they're spending a lot of time doing license management, BIOS updates, trying to figure out where that network latency issue came from, and those things go away in the public cloud. So,
but how is that any different than the developer who's being forced to move from AWS to Google? Because those two APIs are not the same.
For sure.
So anytime you switch your cloud, whether it's on-prem or another cloud vendor, you're telling the developers they have to change their APIs, and those vendors are having the same stack to deal with as we will on-prem. So I'm not seeing what the difference is here.
Well, so in the public cloud, a lot of the APIs you will use as a developer, and a bunch of APIs you don't see that are part of that infrastructure automation. So that is what is driving a bunch of the software automation that is happening in cloud hyperscaler systems that are not present on premises, that have to be hand wired, that have to be hand managed. So there is, if one is changing from a cloud provider to another cloud provider, there's absolutely going to be different work you have to go do to wire into that. But that is still on kind of first class API infrastructure that looks very different than what you have on premises today. And when you think about building a cloud computer, what does it look like to take what runs in a hyperscaler data center today and deliver that as a product on-prem? There's a couple of absolutes. One, all of the hyperscalers have moved to a rack scale design. They've moved away from the pizza box, the 1U, 2U, and they've done that for a couple of reasons. One, because they could. So at one point they said, hey, the design of the system now, kind of like the constraint can be the rack. And now we want to look at how do we get the best density, energy efficiency, and operability out of a rack level computer. And they did things like go to a DC bus bar. So I don't know if folks on the stream won't be able to see, but in Oxide Computer, much like in a rack that runs in a cloud hyperscaler, you've got a copper DC bus bar that feeds a power shelf that rectifies in one place to go to the systems. You don't have that waterfall of 64 power cables pouring off the back of the rack. You have gone to you can choose kind of the height of the chassis that you are designing. A cloud control plane is baked in. And this is a really difficult part of cloud computing. Again, a lot of the team members here at Oxide are on their second or third control plane. And getting this right is critical, because this is what underpins the ability to have elasticity in the infrastructure, the ability to have true multi-tenancy, which is something that is one of the more difficult aspects of a cloud control plane, and what is going to allow you to do bin packing and get to the utilization rates that you want. And the third piece is building the network and into the rack level system and designing security in. And we'll talk a little bit more about that. We built our own switch. It was at the very beginning of the company, we had kind of open question about what to do about the switch. Do we build our own? We're already doing a de novo server sled build. We're taking on a lot. What do we do about the switch? We talked to a very senior person at one of the major cloud hyperscaler providers, and he had said that cloud provider didn't stand on their own 2 feet until they built their own switch into the rack level system. That's when things really opened up from a performance, observability, and control perspective. And then there are security primitives that start with hardware root of trust and being able to have attestation in a true multi-tenant system that is kind of an entry point for being able to build a cloud computer. So at Oxide, we set out to, again, build this system from first principles and asking the same questions that Facebook did in 2008, 2009, which is, if we are going to build a computer that is going to stand up to power cloud computing, what are the right decision points to start from? And one of the earliest ones was geometry. What is the height and the width of the sled? I don't know if you've seen the Facebook Tioga Pass. It's a thinner, their first generation was kind of a 3 wide, thinner sled. We landed on this design for a couple of reasons. One, the height, it's a 100 millimeter tall sled, and this is so that we can get into 80 millimeter fans. The efficiency of a fan is the cube of the radius, and so you end up going from a 20 millimeter fan, those screamers, where you have to have ear protection in the data center, to an 80 millimeter fan, and you get an exponential gain in energy efficiency. So if you look at a rack, we actually have one in the back that we were developing on before we had our own hardware, but a standard rack in an enterprise data center, 25% of the power of that rack is going to the cooling of those fans, both the fans in the chassis and the fans in the AC power supplies. We've been able to go to a design that takes that down to 1.2%. So a 12x improvement in energy efficiency, not just by the choice of fan, but because we control both hardware and software, we were able to do things like do our own PowerShelf controller board. And so this PSC was built by Oxide, and we asked Murata if we were able to go do our own printed circuit board so that not only would we have this air-cooled, more efficient system, but we would be able to capture all the telemetry in power in the system so that in software, we can start to understand what's using what power. And what that leads to is our ability to go do things like power capping, go do things like dynamic power orchestration, and being able to do kind of serve one of the critical areas in on-premises today, which is this power crisis, folks being out of power. The other thing when you operate at the rack level, again, is being able to have this pool of resources. So all of these sleds, this is a server sled. This server sled has 64 cores of CPU in it. You can have up to a terabyte of DRAM. You've got 30 terabytes of NVMe on the front, and then blind mates in the back. So we've blind mated power and networking. So, there were a few things that were great about blades. I don't know how many of you spent time working with blade systems. But one nice thing was the fact that it was very easy to add capacity and it was very easy to service. And you already get blind mating of power with the copper bus bar. This is how the hyperscalers have all of their systems operational. We were able to take it a step further and be able to blind mate the network as well. So this is a cableless server. A technician walks up in the cold aisle in the front. You need more capacity. We can overnight you a sled. You snap it into this system, and then the software will take care of the rest. The software will then go do its security attestation to make sure that is a known good sled, and then it will pull that capacity into the pool. And now your operations team that said we're at 78%, 82% capacity, all of a sudden that capacity limit goes up. So that blind mate nature is both a benefit from an operations perspective, but also being able to have a customer who can now start with a certain level of capacity and then grow on demand, not quite to the level of swiping a credit card and going in the cloud, but much, much, much better than the condition today, where it's a bunch of boxes show up in rack rails, and as we heard from customers, it can be 2 to 3 months from the time boxes land to when developers are actually deploying instances. With Oxide, we can wheel this into the data center, and within hours, you apply network, apply power, within hours, developers are productive.
So are you picturing kind of service of these as benchtop service, where technician goes in, pulls the entire unit out, brings it back somewhere, and either services or upgrades and slots another one in? Or is it still kind of within the rack?
No, you would service benchtop if need be. It depends on what needs to be serviced. So if it is the fan tray, we've got this, the fan tray comes out, we would replace the fan tray, we would replace DIMMs, we would replace NVMe on the front. Anything beyond that, then we do a sled swap.
So the sled becomes the FRU?
There are definitely FRUs that are on the system that are smaller than the sled. For sure, like an NVMe drive,
right,
or a DIMM. But at a certain point, if it was not a condition of one of those components, then yeah, you swap the sled. That's right. The system, again, it's easy to kind of concentrate on the hardware because it is very tangible and physical. But really a lot of what is built in here is in software. We're doing more in software than hardware. Just at an aggregate, you've got over 2,000 cores, and our first generation is built on AMD Milan, up to 32 terabytes of DRAM, a petabyte of NVMe. There's an elastic storage service, which we'll talk about in a moment, that stores everything in triplicate. So you have a couple hundred terabytes of NVMe storage, and comes with 2 middle-of-rack switches that can do a total of 12.8 terabit. And the thing to note is that average rack that I mentioned that has got 25% of its power going to fans, we've been talking to customers. They have about 1,100, 1,200 CPU cores in that rack doing on the order of like 12, 13 kW. And this will do for over 2,000 CPU cores that same power footprint.
Did you look at Bergamo?
We did. We're actually designing our next sled on Turin. And
Right, okay.
Yep.
That's skipping a generation, but
Yeah, we were kind of looking at like density per watt, and that was a really important metric for our customers because, we found the 7713P is the processor that we have in this system, and just hit a real sweet spot for like performance, density per watt. For our Turin systems, we're actually going to go to 4 SKUs. So we're going to have, I don't know if you've seen the dense Turin.
Yeah.
172 cores.
that's why I thought of Bergamo, because it's 4C, which is the
Yep.
dense core architecture. What kind of test bench were you using? Was it spec in, spec FB, that kind of just sort of standard stuff?
Yeah.
Okay.
And this just happened to hit the sweet spot for general purpose compute, which is really what folks wanted, a EC2, EBS, VPC pool of resources. And this particular processor hit the mark on that. Talked about the rack level energy.
Real quickly, before
Yeah,
we
please.
get into that, I was just thinking about this. The big elephant in the room is, of course, AI. Is there plans to support coprocessors in some form or another?
Yeah, we absolutely will have a hardware acceleration product in the limit.
Mm-hmm.
In a way, we are supporting AI today. In a couple of ways, we've got customers that have. You can think about feeder systems and associated application infrastructure that feeds either HPC, AI infrastructure, or other. And we're also seeing that now, as models are getting smaller, you are getting more things at the edge that are actually being done on compute. And this is where like dense Turin and AVX 512 and those things come into play that start to get pretty interesting. So
I was a big fan of the 4C. It really, I think it's mostly been successful for AMD with the 8004.
Yeah.
Which is a different kind of CPU, but that particular microarchitecture does a lot of work by fitting the same pathways for the most part into 1/4 of the size. And I thought that their energy efficiency really was outstanding for Bergamo. But
Yeah.
there's a few little tricks they had to do that.
That's right. That's right.
Made
We've
FD
been very fortunate to work deeply with AMD on
Yeah.
the Turin product, which we think both from a security perspective, performance perspective, is going to be pretty exciting. I want to mention just briefly, by way of building the switch in, and we wrote our own P4 compiler. If you're not familiar with P4, it's programming language around networking. It has given us the power to make the entire network stack fully programmable, so we can do things like. We created this delay-driven multipath that it comes as part of the product. This basically creates a latency graph of all the packets in the system, feeds that back and says for the next packet, what's the least congested path to be able to send that packet. So it's this constantly getting smarter system that is sending packets to the lowest congestion path. There's some other things we've done in that, but effectively what customers are looking for is the end result. You roll this in, plug it in, and expose this to these development teams that have been operating at the end of kind of earlier era infrastructure orchestration. And now all of a sudden they're getting what looks like the elastic compute infrastructure that they love to use in the public cloud. So this ability to select various instance types based on what they care about, what they want, have those things be programmatically provisioned via Terraform or whatever, UI, CLI, API, having the liberty to be able to kind of automate what they're doing and then have the kind of metrics and monitoring that they have in the cloud. An elastic storage service. So this entire rack of NVMe is pooled up and served up as an elastic storage service. So you can snap arbitrary disks to those VMs and has the underpinnings that you would expect for live migrations. You can update the system without downtime. That has the capabilities that allow for snapshotting for customers. And then finally, a set of networking and security services that would be akin to VPC. And the thrust of this is to give developers self-service, allow developers to control their infrastructure environment so they can go do their virtual firewalls, so that they can go manage the virtual IPs and be able to go at a much, much, much faster pace than they have previously had before on-prem. We got a lot more to talk about, hardware, software. We're going to get even further into the guts of this. So apologies for the breeze through a bit of it, but I'm going to turn it over to my colleague and co-founder, Brian
Before you
Cantor.
do, I mean,
Yeah.
the question I have, like the hardware, it's very interesting and all that. The question I have is about the software. The software is all open source, so you're not selling it, you're not licensing it.
You buy the computer, there's no license fees that come with it, which is a novel idea for a lot of folks.
You make money this way, I guess is the question.
Great question. Yeah, it turns out, you could also ask the question of NVIDIA and Apple and Tesla and some others. But when you're shipping a product that delivers public cloud value to customers in an economic profile that is far better than public cloud rental rates, it turns out, yes, you can have a profitable business that is delivering this hardware, software, co-design artifact. Hardware is the delivery vehicle for our open source software, and our customers have been delighted that at these current levels that they're able to have a good economic story and also get cloud computing.
All the companies mentioned, NVIDIA, Tesla, they're all charging hardware and software license.
I don't pay a software license fee from Apple, but
Maybe.
yeah, I don't know that I don't have a Tesla, but a coworker of ours does, and I think there's an option to pay for the software. But no, we believe that, again, and this kind of comes out of our past, that like when you buy the computer, it should come with all the software required to run it. It should come with all the software required to run the cloud. And so the model, just to close, is a CapEx model. You purchase the system, and then we have a support subscription, which is like a warranty, and software update that is recurring.
But it's not managed.
life
It's
cycle to be.
On the rack, we think it's 7 to 10 year useful life. Like, mileage will vary per customer. The switches, we think we're designing those around like 5 to 7 year useful life. And sleds, I ran systems for 7-8 years back when I was running a public cloud. It's one of the nice things about owning your cloud is you get to choose your depreciation schedule. I don't know if you saw the Amazon announcement. Financial engineering to pull $1 billion back in. Customers didn't see a dime of that. But we definitely think, especially with the slowing of Moore's law, you can get a lot of useful life out of these things.